here what we're going to do is I'm going to present you with a few examples where we're going to look at using proof by contradiction in order to prove statements. What I want you to do is I want you to read the 4 examples, pause the video, go away and have a crack at them, and then come back and compare your working with the working I'm going to present here in order to show you. Let's have a look at the questions. So the 4 that I've got here, prove that root 3 is irrational. If I give you that root 5 is irrational, prove that 7 plus 2 root 5 is irrational. Prove that if 5n is even, then n is odd. And prove that log to the base 5 of 10 is irrational. So pause just now and go and have a crack at each of these questions and then come back and have a look. The first question here, prove that root 3 is irrational. First thing we have to do is come up with our contradiction. Well, if the question is prove root 3 is irrational, what that means is that my contradiction is that I want to assume that root 3 is rational. What do I mean by that? Well, that means that root 3 can be written in the form of a over b, and the key thing here is that a and b have no common factors. Think of it in the most simple of terms as being a fraction in its simplest form. I can write root 3 like that. Now, if I have root 3 equals a over b, I can work with that and play about with it to see where I can get to. If I square both sides of that, what I'm then able to say is fine, then 3 is equal to a squared over b squared. Rearranging that means that I can write that a squared is equal to 3 times b squared. Now that tells me that a squared is a multiple of 3. So if a squared is a multiple of 3, a itself is a multiple of 3. So this here has the implication that a is equal to the multiple of 3, so let's call it 3k. Multiples of 3, we'll always take that format. So if I substitute that back in there, what that then means is that I can say that 3k squared is equal to 3b squared. If I square it the left-hand side, I get that 9k squared is equal to 3b squared. Divide through by 3, and I get that b squared is equal to 3k squared. What that means then is that b squared is a multiple of 3, therefore b is a multiple of 3. So b can be written in a format of 3 times something which we'll call t. So this here has the implication that both a and b are multiples of 3. And if a and b are multiples of 3, the number is not rational. So because that number is not rational, that means that root 3 is irrational. This here cannot hold if my contradictory statement here of root 3 being rational is true. So I contradict my contradiction, which means that the original statement is true. Think of the format of the numbers, and that leads you there over a few steps. Second question was that given root 5 is irrational, I want to prove that 7 plus 2 root 5 is also irrational. So to start with this one, I need to come up with my contradiction. Now my contradiction is going to centre around this statement here, that 7 plus 2 root 5 is irrational, because that's like the ultimate goal. So if I'm wanting to prove that 7 plus 2 root 5 is irrational, what I'm going to do is I'm going to come up with a contradictory statement that says assume 7 plus 2 root 5 is rational. And I'm going to work from there. This part here, that root 5 is irrational, has been stated and is given. Root 5 is an irrational number, so we don't work on that. We're looking at the result and the outcome. So if I assume that 7 plus 2 root 5 is rational, that means that 7 plus 2 root 5 takes the format of a over b. Now I can start to manipulate that, because what I can then do is say that 2 root 5 is equal to a over b, take away 7. And if I simplify that on that side, that means that I've got a take away 7b all over b. If I then divide through by 2, I get root 5 is equal to a minus 7b over 2b. What that then means is that root 5 here is a rational number. So in this format, root 5 is a rational number. But hang on, back at the start, it tells me root 5 is irrational. And that doesn't make sense, because it's telling me that I have a rational and an irrational number both at the same time. Doesn't work. Doesn't work that way. So what I've done is I've contradicted this contradiction that's here, and I can say fine, therefore that means my original statement is true. So I've contradicted the contradiction and proven the original conjecture itself. This one here asks me to prove that if 5n is even, then n is odd. So my contradiction in this one here is that assume that 5n is even, then n is even. So what that means is, if I assume 5n is even, that then means that 5n is equal to something of the format of 2k. Then n is equal to 2k divided by 5. However, at this part of my contradiction, I'm saying that n is even. So what that means then is that n is going to take some format of 2 times t. Well, those don't match up. N can't be 2k over 5 and 2t at the same time. So what that means then is the contradiction is contradicted, so the original statement is true. A nice one to go through, and again it's just looking at the formatting of numbers and the way that they're set up, how we write even numbers, odd numbers, multiples of 5, etc. The last example I'm going to work through here is that I want to prove that log to the base 5 of 10 is irrational. So my contradictory statement for that one is that I'm then going to say fine, so I'm going to assume log to the base 5 of 10 is rational. What that means is I can write it in the format of log to the base 5 of 10 is equal to a over b. Now, if I start using laws of logarithms in order to manipulate this, I can take the base across and rewrite that as 10 is equal to 5 to the power of a over b. So I can start by manipulating it in that manner there. What I'm then going to do is raise both sides to the power of b to get rid of the fractional power there. So I can say fine, that means 10 to the power of b is equal to 5 to the power of a. Now, if I'm going to manipulate a 10 to the power of b, I'll just do this across here. That's the equivalent of me saying 2 times 5 to the power of b. And again, I'm going to use the laws of indices to expand that and make sure that that's written as 2 to the b times 5 to the b. So I can then go back and rewrite it as 2 to the power of b times 5 to the power of b is equal to 5 to the power of a. So if I then take this 5 back across here, I'm essentially saying that 2 to the power of b is equal to 5 to the power of a minus b. Now, how does this help me? Well, 2 to the power of b is always, always, always going to be even. 5 to the power of a minus b is always going to be odd. And the thing that comes from the bottom of all of this is that 2 and 5 are primes, so there's no integer powers and no integer values for a and b such that this holds. So that cannot be true for integer values of a and b, which are part of what we need in order for this fraction here to hold, the a over b, and for it to be rational. So this contradicts the fact that we assume log to the base 5 of 10 is rational. So it contradicts the contradiction, and that then means that the original is true. We have to make sure we can explain this, and that's the type of explanation we need. Look at number relations. Big things to remember when we're doing this is talking about formats of rational numbers, formats of even numbers, formats of odd numbers, formats of multiples of certain types, i.e. multiples of 3, like we had in one of the previous examples. Remember all of this number theory behind it, bring it all together and use your communication in order to effectively communicate what you are doing and how that comes across. And just remember how to make an assumption and how to make a contradictory statement. We go from if P then Q to assume P not Q. We have to bear that in mind, and we have to work with that when doing contradiction.